Welcome and thank you all for joining us today. My name is Brielle and I'm one of the organizers for this year's Quantitative seminar series for the Converse Lab. And I'll begin by acknowledging the Coast Salish peoples of this land, the land which touches the shared waters of all tribes and bands within the Suquamish, Tulalip, and Muckleshoot nations. We also acknowledge that we live and work on the ancestral lands of the Duwamish people, the first people of Seattle. So I'm very excited to introduce our speaker today, Xingli Giam. Xingli is an assistant professor in the Department of Ecology and Evolutionary Biology at the University of Tennessee, Knoxville. He completed his bachelor's and master's in biology at the National University of Singapore in 2007 and 2010. He received his PhD in ecology and evolutionary biology at Princeton University in 2014. And after completing his PhD research on freshwater fish conservation in Southeast Asia, he conducted research centering on freshwater fish macroecology and statistical ecology as a postdoc at the University of Washington. So his research at University of Tennessee focuses on characterizing and mitigating anthropogenic impacts on the environment with an emphasis on tropical and freshwater systems. His research leverages on large-scale, continental-scale environmental, biological, and socioeconomic data sets to answer policy-relevant questions in conservation at multiple spatial scales. So these projects span multiple ecological and human systems, including climate change, non-native species impacts in the southern Appalachias, aquatic macroecology of the US and Southeast Asia, and land cover and use change in Southeast Asia. So that's Xingli, and I will let you take that away. Thanks, everyone.
Thanks, Brielle, for the introduction. So it's really nice to be back, albeit virtually, on Northeast Bolt Street. So I was a postdoc here at UW from 2014 to 2016. And then I started my position here at the University of Tennessee. So today I'm going to talk a little bit about some of the work that I've done on kind of looking at the drivers of deforestation. And particularly, I would like to focus on China's Belt and Road Initiative. But before I start that, I just want to kind of like introduce myself a little bit on what I do at the University of Tennessee. So basically, we do a lot of aquatic conservation science and macroecology here. And here you can see, we combine kind of like field work, and then we also look at the impacts of mining from collating information from different data sources. With field and experimental work, we look at the impacts of climate change on different species of fish. Here we've got 2 species of darters, and we do a lot of like large-scale kind of projecting impacts on the work. Here we kind of projected how the dispersal velocity of fish would vary across the different stream reaches in the southern Appalachians. So the focus of the group, as I was saying, is on conservation science. Well, mainly focusing on aquatic stream systems. And I'm so sorry that I'm not gonna like the focus of this talk is not quite on aquatic systems. But I'll give you some sneak preview of that. Like I can't come to SAPS and give a talk without like talking about fish. So I'm gonna do that. And then like the second part, I work deals with a lot of macroecology, so looking at ecological processes, kind of driving regional to continental scale patterns, and this includes like productivity gradients, body size gradients, and what are some of the drivers of community assembly, like what determines where species occur at a given time. And then the main approaches would be kind of just collating and analyzing existing publicly available data sets from papers as well as from agencies. And I like to use like statistical approaches from various fields, including social science and like economics. So in the deforestation analysis that I'll be presenting today, like the main approach is actually borrowed from the field of social science. Which is really cool, and I'm really excited to present. And I collaborate a lot with scientists from universities as well as agencies. I think the agency collaboration is something that I really enjoy. Working with folks out here in Tennessee, from the Tennessee Valley Authority, as well as from TWRA and different NGOs. You really get to understand what are their management needs and their scientific needs. So we aim to kind of do science that can actually kind of inform what these management agencies do from day to day. So as I was saying, we also do some experimental and field work, but we do experimental and field work when it's needed. Because most of the time, a lot of the data has been collected by agencies. So, we don't really want to reinvent the wheel or spend extra money to collect data that might actually already be there. Right. So just quickly, as an aside to what the main project I'm going to present, as I was saying, I've given a talk to Seth, so there's no way I could get away with not talking about some of my fish work at least. So, I'd like to introduce some of my projects that I've done with apps where we look at the effect of climate change and how that affects fish in Appalachians. So the question we always would have, when we come to a new place is that, when I took up this job, I was like, the Appalachians is such a beautiful area. There's a large, broad elevational gradient, and there are so many species of streamfish, and many of these species are actually endemic to this area or endemic to a few basins within the southern Appalachians. So one question I have is, we wanted to ask, can streamfish actually keep pace with climate change in this area? And so for this project, we kind of invoke the concept of climate velocity. So climate velocity is the speed at which an organism would have to travel or move to arrive at a new location with the same climate as its previous location. So if you just look at these two cartoons, there's like a stream network, and thicker lines meaning more water, thinner lines meaning less water. So the thicker lines mean that this is like a main stem, and then there's a trip here. And let's say these two cartoons represent current conditions or contemporary conditions and then future conditions. And of course, from like a kind of like downstream to upstream, we know that temperature would decrease, right, from downstream to upstream. As it goes higher up in elevation, typically temperature decreases, becomes cooler. But if it's like all of you should know that when we travel upstream like a main stem, typically the reductions in temperature occurs more slowly, or it occurs across a greater distance than if we go up a trip, because sometimes the trip typically flows down a higher elevation area, right? So you might see like kind of a more abrupt change in temperature or lowering of temperature as you go from the main stem here to the tree. So imagine that over the course of 100 years, let's assume that the water temperature increases by 2 degrees Celsius across each of these stream reaches, right? For a species that originally occurred here in this lowest reach of the main stem at 23 degrees Celsius, there are two ways that it could move to kind of maintain the same environmental conditions of the same environment. It could move to this tree, which is nearer, or it could move up the main stem, which is further. So in this case, right, where a fish is going to move would affect how fast it will need to move to maintain the same temperature. So kind of this is the concept of climate velocity, where a fish would really have to move really quickly in order to reach this habitat. However, if it chooses the tributary habitat, it would have it would not need to move as fast. Right. So very quickly, we then use the concept of net dispersal velocity, where net dispersal velocity (NDV) is equal to dispersal velocity minus the climate velocity. So remember that climate velocity is the speed at which the species will need to move. Dispersal velocity is actually the speed at which the species can actually move. Fish can. So if the fish can move faster than what the speed it needs to move at, then it's positive, right? So it means that the fish can move faster than needed to reach climatically suitable habitat. Negative NDV means that the fish now it moves slower than needed. Like its dispersal velocity is lower than the climate velocity. So it's negative and it doesn't move as fast as required. So if the NDV is positive, it means that the fish can find suitable habitat conditions, defined as habitat conditions that were the same as before. But with negative NDV, it means that the fish will not be able to move to keep pace with climate change. So using this concept, we use a model of a trait-based model to predict how fast a species can actually move, the dispersal velocity, and then using GIS, we calculated the climate velocity across extreme regions as well. And that allowed us to calculate what is the net dispersal velocity. So again, if it's positive, it means that it's really good, the fish can actually move, disperse to climatically suitable streams and can survive. It's negative, means that's pretty bad. So here, there are two dispersal pathways as I was talking about. One is along the trip and one is along the main stem. Right? So you can see that typically along the trip, the net dispersal velocity as expected tends to be a little bit higher than if it's going through the main stem. Right? So this goes back to this hypothesis that we have, because of the gradient of the main stem typically is a lot more less steep and more gentle than the pathway from the main stem to the tree. It means that here the climate velocity is much higher if the fish were to disperse from this ridge over to this ridge than it would be if the fish disperses from this ridge to this particular tributary. Therefore, you see the net dispersal velocity being like positive here along the trips, more positive than along the main stem. So we divided up the populations into mobile populations and stationary populations because the previous meta-analysis has found that typically dispersal distances in a given species tend to be bimodal. So within a population, there are always species that tend to, they're more adventurous in behavior, they tend to move further away from their, or have a larger home range, whereas like there are members of a population or subpopulation that's more stationary. So if you compare the mobile and the stationary subpopulations, you see that of course the mobile populations would have typically a higher net dispersal velocity because the dispersal velocity is really high. Well, what's interesting here is the trade-off between when climate change occurs and the fish chooses to move either along a trade or along the main stem. There's a trade-off between whether the fish can actually reach an area or reach versus whether the fish can actually survive in that area. So you can see that along the trade, the net dispersal velocity is positive, which means that the fish can actually reach. They can disperse far enough and they can keep pace with climate change. Whereas along the main stem, typically for many of the fishes, it tend to be negative, meaning that it cannot keep pace. But if you look at change in habitat suitability, so this is a SDM species distribution model based change in habitat suitability that is just based on the physical habitat, which means the size of the stream, based on the substrate, based on the slope and the elevation, etc. So those variables go into the model. You'll see that if we go along a trade, for a lot of fishes, there's a high change in habitat suitability of up to like 50%. Mostly, most species don't experience a change in habitat suitability as high as a decrease by 50%, but it's still a pretty big decrease compared to along the main stem. So here, there's a trade-off. The trips are really good, right? They would probably represent the climate of the future for many of these species, but yet, if the species goes there, there might be issues with survival based on a decline in the suitability of the habitat. So we could use this information and we could kind of like map it across. cross all the streams in the southern Appalachians, and we could see exactly where, how these effects emerge across the landscape. So I thought that was pretty cool, and just wanted to like present a little bit of my work, since I'm presenting to a set audience. Right. So I can't see, I actually can't see anything but my presentation. I can't see my face either, so I don't know how I look or if I'm looking at the right spot. So is everything all right? Can everyone hear me? Good. All right.
Yeah, we can hear you well.
Okay, great. All right. So for the second part of the talk, I'm going to talk about the main question: will China's Belt and Road Initiative increase tropical deforestation? So before I start, I really want to kind of acknowledge my collaborators and co-authors on this paper. So first, I want to acknowledge Dr. Luis Carrasco. He was a NIMBIOS and UTK EEB postdoc, and now he's a research scientist at Descartes Labs. And then Dr. Charlotte Chang, she was a NIMBIOS postdoc fellow, and now she's an assistant professor at Pomona College. And both of them are, they really contributed to this analysis, and would like to acknowledge that. This work would not be possible without their participation. And then, of course, I'd like to acknowledge NIMBIOS and EEB as well in the University of Texas. So just an introduction on China's Belt and Road Initiative. So in September 7th, 2013, so almost 10 years ago, presidency of China in Astana, Kazakhstan, first talked about cooperation between China and Central Asia to build an economic belt along the Silk Road. And that is to forge, just to quote his speech, is to forge closer economic ties, deepen cooperation, and expand development space in the Eurasian region. And you notice that he used the language Silk Road, and basically this invoked the history of the ancient Silk Road as a link between the East and the West. So the link between Far Eastern Asia and the Middle East and Europe, as like a historical trading route. And then in the same year, in Jakarta, Indonesia, the presidency talked about cooperation between China and ASEAN. So ASEAN is an association of Southeast Asian nations. So these are countries in Southeast Asia like Indonesia, Malaysia, Singapore, Thailand, Myanmar, Vietnam. So these countries form this association of Southeast Asian nations, and he talked about the cooperation between China and this association to build a 21st century maritime system. So if you notice, here in Kazakhstan, we talk about more of a land route, right? Kind of across Central Asia, just a link between China and the Middle East, Central Asia, and Europe. And in Indonesia, because Southeast Asia is like a kind of it's an insular region. It's a region with a lot of islands, a lot of water. They talked about building a maritime city. And he proposed the Asian Infrastructure Investment Bank. So like a new bank, like kind of to rival the World Bank, to help to fund various projects in Asia. And it's for the benefit of common development and prosperity. And as before, there was a historical reference as well. He referenced Zheng He, who is a historical figure in the 14th and 15th century. So in early 15th century, he was an admiral that sailed to various different parts of Southeast Asia, including Malaysia and Indonesia, and created a lot of trade connections between then China and nations and cities in Southeast Asia. So in 2013 and 2016, this initiative is called One Belt, One Road. So belt meaning is land trade routes, and road meaning maritime trade routes. And then since 2016, it changed from One Belt, One Road to Belt and Road Initiative, and BRI. So at this point of time, even now, is known as the BRI. Is a more common term, and the change reflects the fact that at first I think the idea was to build like one single connection or a few connections, but since 2016 it expanded such that now the Belt and Road Initiative emphasizes multiple projects and the integrated nature of land and maritime projects. So basically, if China were to find like a new port in certain parts of let's say like South Asia, right? Like in India or in Pakistan, then there will also be a road that might connect the port to other trade routes on land. So it has become more integrated and larger. So these infrastructure projects include rail systems, highways, bridges, ports, pipelines that transport like fuels of gas, and then it also includes electric grids as well, power plants. Most of these projects were funded by China's state-owned banks and contractors. Some of it is funded by the Asian Infrastructure Bank, and the end date for the BRI is 2050 or 2029. So we have some ways to go. So what are the implications of BRI on tropical deforestation? As of January 2020, 137 countries have signed cooperation documents. So it's interesting, right? Why January 2020? What happened in January 2020, right? It's kind of the start of the pandemic. So since then, like a lot of like global trade and movement has actually like slowed down a lot. So since then, I'm not sure if there's any increase in the number of countries. They haven't announced any yet. But this point is such that it's a pretty big program where the large majority of the world's countries have actually signed some kind of cooperation documents, meaning that they are planning for the investment of the Chinese government to build roads or to build infrastructure. Many of these countries are tropical countries with intact forests. Some are not intact forests. And currently there are two existing analyses. One is a blog post and the other is a paper in ConBio, kind of looking at perhaps the potential effects of the BRI, the Belt and Road Initiative, on tropical deforestation. But they basically consider only currently planned routes. So if you look at this map from the previous slide, there's some information on where the routes are. So what this analysis did was that they overlaid the routes onto like a land cover map, and they make assumptions like if you were to build like a new road like that or pipeline, how much forest at each side of the pipeline would such an infrastructure project cause deforestation. So they only consider currently planned routes. But then there's no really centralized database of projects, and because the end date is about 30 years away, there's still probably going to be more projects that can come. So the impact on tropical deforestation is quite unclear, even though previous analyses have, they considered some of these planned routes. But these planned routes are kind of a small minority, I guess, of all the projects that would probably happen by 2020. So this is a map of all the BRI countries. You see that a large part of the Middle East, Central Asia, some parts of Eastern Europe, large parts, many countries in Africa, a lot of countries in Southeast Asia, and some countries in South America as well. They have all signed on to this BRI. So the research question here is, would the Belt and Road Initiative increase tropical deforestation? And because, as I said, there's not a lot of information, publicly available information. It's not very transparent, this program, so we don't know exactly what are the projects that are being planned in the next 10 or 20 years. And of course, some of the projects are still being planned. So we can't really, it'll be really difficult to predict these impacts based on the lack of data. So we took another strategy, and the strategy is to take a more retrospective approach where we looked at previous Chinese developmental aid projects in the last 15 years, right? So kind of like with the assumption that, if the previous projects are going to be similar to the projects that China undertakes in the tropical region, then we could say that the results of the previous project might well reflect what's going to happen in the future. So that's our strategy. We use three key sources of data. One is a data set of primary humid tropical forests. So these are primary rainforests. You can see from the maps here, in the typical regions, we have large parts of Amazon, as well as some Andean forests as well, West Africa, and Southeast Asia. So these are the three main areas of tropical rainforests in the world. And we have a global raster of this forest by in the year 2001. And then there's the second data set is yearly tree cover loss from 2001 to 2017, again produced by the University of Maryland, Hansen Lab. And then the last key source of data, this is a really cool data set, is the data set that's produced by the 8 Data Lab. It's a research lab based in the College of William and Mary in Virginia. And basically, it's a geo-coded Chinese aid data set. So in this data set, the lab and their volunteers and students and research fellows, they would get data from newspapers around the world, newspapers in China, as well as newspapers in many countries to basically extract information on infrastructure projects and when a certain project has started, where is the project, is the project sponsored by China or not, or is the project funded by China. So they basically compile a huge data set of Chinese aid projects. Right. So we use data sets 1 and 2 to calculate forest loss. So the data set 1, the primary rainforest data set, shows where primary rainforest or primary humid tropical forest would be at the start of year 2001. And so it's in the form of 30-meter pixels, because that's the native grain size of Landsat. So because this data set is built from Landsat images. The second data set, right, the yearly tree cover loss data set, shows us the year that the tree cover is lost for each of these pixels. So first, we use the first data set to only select, right, the only primary forest for deforestation analysis. So we are only interested in the loss of tree cover of primary forest that is existing in year 2001. And then using data set 2, which is the tree cover loss data set, we can calculate at the sub-province level globally, at the level of sub-province. So this is the level of roughly the county level in the US for most countries. So we can calculate the sub-province level, the area of forest lost each year from 2001 to 2017. And then we also can calculate the area of forest loss, the area of forest that is standing at the start of each year. So then we can start to kind of get a data set of how much forest is lost, what's the starting amount of forest, and how much was lost in a given year for a given sub-province globally. And we could use an interface called Google Earth Engine to do the raster calculations. So basically, it's like a cloud-based computing system where like anyone can sign up for it. So it's Java-based, and you could use Java code to actually kind of do remote sensing using Landsat images, using different types of satellite images. But there are a lot of other data products, such as the Hansen data sets, the land cover data sets, as well as the tree cover loss data sets that's already ingested into Google Earth Engine. So you could just, with a few lines of code, you could actually make these calculations. And this would be the fastest way of making calculations, actually, because if you were to do it in R, it would be almost impossible because of the really small grain size of the pixels. So the third data set is a Chinese aid data set. So again, it's geo-coded Chinese government finance projects from year 2000 to 2014. Just to specify, there are three main types of finance. So they divide it up into three main types. One is ODA, also called Official Development Assistance. There is concessionality, which means that the Chinese government is giving some money to the country, and this money need not be paid back. So it's more of a grant rather than money that is being lent and needs to be paid back. And then, so this is like defined as official development assistance, because there's some development intent and there's some grant kind of element where money need not be paid back. And then there's also another group of finance called other official finance. It means that it lacks concessionality. Maybe it's a loan that needs to be paid back, but it's still funded by the Chinese government, and they may not have any development intent. And then the third main type is called vague, which means that there's just not enough information available in the media, the newspaper reports to actually classify the project either as ODA or OOF. But to follow this author who has used this data set to look at how Chinese developmental aid projects might have led to So Bloom used this data set to look at how Chinese aid might have led to increasing inequalities within other countries. And Bloom used ODA, OOF, and VIG all together and took these three categories as official finance. So we just follow them by doing the same thing. The projects are classified by sectors. So there's energy sector, there's production, so factories and goods that are being produced. There are projects that are social in nature, like the building of schools and hospitals, things like that. And then there's transportation projects. So this is just the number of projects in gray, or the number of sub-provinces across the world that have received Chinese funding on one or more of these projects. So you see that there are a lot more social projects than other projects, but transportation is like close. It's really close as well. So this is the plot of the number of projects as well as the number of sub-provinces. So on the right is the number of sub-provinces across each year with a project, and the panel on the left shows the number of projects as a function of year. You see that for social projects in pink, energy projects in brown, and production projects in purple, there is like a large increase from year 2000 to about mid-term through our data set, about year 2008, and then there's a small decline. However, for transportation projects, it's the only sector that has seen like a huge increase. And so this is reflective of like the Belt and Road Initiative that was kind of announced by China. So even before China actually announced the Belt and Road project in 2013, like in the 10 or 13 years prior to that, there's really a ramping up of transportation type infrastructure. So I find this to be like really cool. This is a map of the number of years for which there's one or more transportation aid projects in each sub-province. Right. So as I was saying, like each of the dots represent like one given sub-province, and this unit is somewhat similar to the county level, maybe a little bit bigger in some countries, similar to the county level in the US. So here, one out of the 8,738 sub-provinces across areas with primary humid forests. So the gray areas and the colored areas are all the areas or the sub-provinces across the world with tropical humid forests in year 2001. Right, and then most of these sub-provinces did not have any Chinese governmental aid infrastructure projects. So here we're just talking about transportation aid projects, and we focus specifically on transportation aid because we hypothesize that these projects are the ones that would most likely cause deforestation, right? Because if you build roads and you increase accessibility, that will also cause more humans to settle in the area. It also cause the development of industries as well. And so our focus for this project is mostly on transportation. So anyways, you can see that out of 8,000, close to 8,800 sub-provinces, only about 191 actually had transportation projects, which is not that surprising, right? Although China is a big country and has a huge financial clout, there's probably no way it can, help fund projects in a lot of the 8,800 sub-provinces. So I think 200 is probably about right. And of course, I think the data set that is compiled by the College of William and Mary is bound to leave out some projects. So 109 is what we know. Of course, there might be more, maybe 200, maybe 300, but I think this is like a believable number. So in this model, so before going to the modeling part, I would like to introduce this model that we use to try to model deforestation. So we use the within between random effects model, REWB. It's a pretty new model, and it comes from the social science literature, as I was saying. So just as an example, right, the response variable YIT is being modeled as a function of all these parameters here. So if you look, it's quite familiar to you because it's very similar to regression model. So if YIT is the response variable, then the XIT might be a predictor variable that varies with time t in the ith level. So here we're talking about a panel. This is very close to a panel model. So it's used to model a panel model where you might have observations taken at multiple time steps, right? So for every spatial unit or for every person, you might take observations at time equals 1, time equals 2, time equals 3. So here you have response variables that's taken at all these times for each person. So T refers to time and I refers to that person or that spatial unit. So here for our deforestation analysis, right, YIT is the amount of forest that's being lost, so the amount of deforestation at a given year, meaning at time t, for a given sub-province, which is the I, right? So the interesting thing here is that the REWB model actually distinguishes between a within effect and a between effect in the ith unit, which means in our case, and I can explain this a little bit more in the later slides, but in the ith unit, so remember here, the ith unit is a sub-province, and T is just a given year in that particular sub-province. So it tells us, over here, is there particular years where this predictor variable is higher than other years than the average, and could this affect the response variable? And then the average variable here will then tell us, across all years, would the average level of, for instance, the average level of A or the average GDP, would it affect the deforestation rate, right? And then you might have a predictor variable that is time invariant, which means, for instance, the elevation of a spatial unit, because we know the elevation doesn't change with time. So across all the time units, the elevations will stay the same. So ZI might be a variable like that. And then VI might be the random intercept. And EIT is just the observation level residual or average. Right. So just to compare this with some of the models that we use in ecology quite often, just to compare this REWB model with a regular mixed effects model with random intercept, right? So you see that YIT, so for any observation, it can be predicted by the intercept plus the slope multiplied by a given predictor variable, right? And then there might be some kind of a random intercept here where different eyes, so different people or different clusters of spatial units might increase the intercept by a certain level, right? And then some random effects models, some mixed effects models might have both the random intercept and slope. So sometimes you see this in the literature. Most mixed effects models in the literature actually fit only the random intercept. But recent work has shown that it's actually quite important to fit the random slope as well. Because if you don't fit the random slope, you might get overly optimistic p-values. So this random slope just means that the slope itself, the relationship between xit and yit can be modified by what spatial unit it comes from, for instance. And then the REWB model, now for here, it has both the random intercept term as well as the random slope term. So, yeah, right. So again, the REWB model is different because here it estimates average within cluster or within person effect. So how perhaps certain years this particular variable might change through time, and perhaps it might affect the response. And then it breaks it down into this component as well as the average component, where the effect is mostly explained by changes or variation across the cluster or across each person. So one interesting thing, like I like to use this analogy to explain this, is that if like for instance, if we think about in presidential elections, like social science research have shown that in states that are richer, that means states with a higher like household income or some indicator of wealth like that, states like that tend to vote for Democratic presidents most of the time. But within a given state, you find that the richest people tend to vote Republican. So here is, for such a model, for instance, it'll be useful for such a model to actually differentiate, to find this particular effect, where, if you look at voting patterns, you have people within a state, right? But for a given state, the richest people would tend to vote for Republicans. But then if you look at the average person across each state, like a person in a richer state will tend to vote for a Democrat. So it helps to break down the effect to within a spatial unit and across spatial units. And yeah, and so that's quite interesting. So here, just to explain the REWB, the random effects within between model, back to our question. So here we have the response variable is deforestation at a given subprovince I, nested within country J at annual time steps T. So basically it's the same as our IT syntax, but now there's additional J because the subprovince is nested within country. So we modeled deforestation as a function of transportation aid. So whether a subprovince has a transportation aid project or not. We also included another variable, it's called X8. So external aid is where a neighboring subprovince has a project or not. So we are testing for the contagion effect here. Like for instance, we are predicting that deforestation rates can increase even if there's no aid within the subprovince, but if there's aid given to a neighboring subprovince. Because we talk about building transportation infrastructure, it will still bring in people, bring in industries, and it might still cause deforestation in areas that are outside the subprovince of the project itself. And then we've got other variables like GDP. We have the amount of forest to begin with, and of course, the more forest you have, the more likely the forest is going to be deforested, right? So it's a sampling effect kind of thing. And then there's elevation, because we know that low-lying areas are typically more conducive for agriculture, and they tend to be deforested more. So we use a hurdle model because of zeros, a lot of zeros. And first, we model binary deforestation, whether a subprovince is deforested or not. And then second, for the observations with non-zero deforestation, we model the log response ratio of deforestation as a function of all these variables. So just to move on to the results, so we see that 8B means it's a between effect of 8. So the variation across different subprovinces. Across different subprovinces. And then 8W means variation in 8 across the years in a given subprovince. Right, and then there's elevation, and then there's external aid. So just to recap, external aid meaning whether a project was started in a neighboring subprovince or not. So again, between means is variation across the subprovinces. Within means variation of aid across years within the subprovince. And then there's GDP as well, between and within, and the amount of forest. So you see that, of course, when there's more forest, chances are there'll be at least 1 pixel or 2 pixels that will be deforested. So that makes a lot of sense. That it's like one of the strongest variables, because it's just a control. It's just a control variable. It also makes sense that here low-lying areas tend to get deforested more quickly, right? Because a lot of deforested areas, they are really mostly coastal areas or areas that have existing infrastructure. So you would tend to get deforested more as well. And then GDP is interesting. So in sub-provinces or countries, because GDP is actually a country level variable, countries with lower GDP tend to be deforested, tend to have a higher likelihood of deforestation. And another interesting thing is that you look at GDP within, there's some evidence, but it's not significant, it's approaching significance. So you can see that the 95% confidence interval barely overlaps with 0. It tells us that even within certain years, in years where the country is not doing that well, where GDP production is lower, within a sub-province or within a country, deforestation tends to be higher. So this itself is an interesting finding, but it's barely significant. So I'm not going to stress that, but it's just something that's interesting. In the second part of the hurdle model, we are predicting the amount of deforestation among the sub-provinces that have experienced at least some deforestation. So before that, we were trying to predict yes or no, was that deforestation? Now we're trying to predict how much deforestation there is. So we see that A has effect, right? So here, A within a given period. So in years where 8 is given, for a given subprovince, it actually increased deforestation rates. And then, so we see the same thing with elevation, and then we see an interesting effect with external aid as well. So external aid, again, means whether a transportation aid project was initiated in a subprovince that is neighboring to the focal province. So it shows some contagion effects there. Even if a neighboring subprovince has a transportation aid project, it will cause increased deforestation in another province close to it. So we see the same GDP effect, and here this is interesting. We see a negative forest effect, and again, this is just a control variable, so I'm not going to read too much into it. But basically, they're saying that in sub-provinces with a lot more forest, we are actually deforesting less, which is interesting. So the conclusions was that compared to sub-provinces that did not lose forest in a given year, sub-provinces that lost some forest, so this is the first part of the hurdle, they had more forest to begin with, they were at lower elevation, and they had lower per capita GDP average across years. So poorer countries tend to deforest more, sub-provinces and the lower elevations tend to deforest more, and sub-provinces that have forests tend to be deforested. And then for the hurdle 2, when we are trying to predict for the actual amount of deforestation that's taking place. Sub-provinces at a lower elevation again, so this consistent, has lost more forests, greater proportion of forests. Sub-provinces that had transportation aid projects in neighboring provinces 2 years prior. So I forgot to mention that all the aid projects, we use a 2-year lag because we found that there's a 2-year lag between the project that was announced versus the project that's completed. That's why we use a 2-year lag. And also consistently with the first hurdle, is consistent with the first hurdle model, countries with a lower GDP, average across years, they tend to have lost more forests as well. And again, sub-provinces with transportation aid projects in their own sub-province tends to be deforested more. Sorry about that. So the conclusions is that we found that Chinese transportation aid is linked to deforestation in the sub-province of the project. So it's either due to direct forest loss due to the project itself, also due to increased accessibility. This is something that we can't really tell from the scale of analysis because we just don't have enough data. So it can be due to just the fact that the forests are being cleared to build the roads or to build the port, or it might be due to increased accessibility. But at least the contagion effect, which means that the neighboring sub-provinces, a project in neighboring sub-provinces increase deforestation rates in another sub-province, it provides evidence for some kind of like accessibility. Like we have roads, we have ports or whatever. You're bringing in, you're causing the economy to go in overdrive. You're bringing in more people to remove the forest. So if the Belt and Road Initiative were to follow similar trajectories or paths as 8 projects over the last 10 years, we think deforestation rates may increase. And just some kind of, when some kind of modeling considerations, like I tend to go into the weeds a lot. You all can ask Julian and tell you more. I tend to go way into the weeds. We talked a little bit about random slopes model being more conservative. So in these areas, in the models that we use, we actually fit random slope models. So all the p-values that you see are pretty conservative, which means that if we don't fit random slopes, what happens is that all these values might go higher and it might be more significant. So fitting random slopes model is good because it's more conservative. It results in higher p-values. There are some issues with long tails. So one solution would be to fit Bayesian models with t-distribution errors, perhaps, or to do something that is very common in the social economic literature, which is to use propensity score matching. But that would also mean perhaps collapsing all the deforestation rates from a yearly basis to like to a decadal basis. So that's all I have. I'm sorry, I think I went above time by a few minutes, but if you have any questions, I would love to answer. Thank you so much.
Thank you so much, Xingli. That was a really cool talk. It was, yeah, I liked that, the in-between random effect model. It seemed pretty elegant. And I liked your analogy with the political way to describe the model as well. That really helped. Yeah, so as a reminder for people, if you have any questions, you can put them into the questions box, or you can raise your hand and I can unmute you. And yeah, so if you have any questions, you can put them down. I guess to start, I have a question about, I guess, kind of your results. Maybe in the second, yeah, that one. I was wondering if you could maybe you already described this, but I was a little confused about the opposite effect of the aid and GDP. Could you maybe describe that again?
Yeah, okay. So GDP means that if GDP has a negative effect on deforestation, it means that sub-provinces because GDP is a country level variable. So we do have GDP for each country, but at a yearly timestamp. So here GDP between means is basically an average GDP across all those years in a given country. So countries, sub-provinces in countries that are poorer, so lower GDP, would tend to have higher deforestation rates.
Mm.
So basically it means that, you know, a lot of it's basically a classic finding where a lot of the poorer countries, they would have to sacrifice their natural resources, right, in order to maybe boost their country's like kind of economic condition. So it's an issue in a lot of tropical like countries where the economic condition is not that good, and really the easiest way for the countries to actually invite investment is to use the natural resources. So in this case, I think forest is one of the big issues. And then for aid, so aid basically here, it means that within a given sub-province, within a sub-province, I didn't mean to make this more red and you just popped up, but
No worries.
within a given sub-province, in years in which there is a transportation aid project that correlated positively with the amount of forest that was deforested. So whenever there's aid project coming from China, you see an increase in deforestation 2 years after the aid project. Yeah, so with external aid, it's the same thing, because this aid variable just means whether that particular sub-province has an aid project. EXPA means whether a neighboring sub-province has the aid project. So because for some provinces that have experienced deforestation, they may not have aid projects in that province itself, but then the likelihood of being deforested increases when a neighboring sub-province has an aid project. So it tells us there's some effect of like roads or infrastructure that's being built in, even if it's not within that focal province, sub-province. If it's in a neighboring sub-province, it might be able to bring in some of this economic activity into the neighboring province and increase its deforestation rates. So it supports the accessibility hypothesis, and it's not just saying that, oh, the project that's being built is causing the deforestation. It's more like even beyond deforesting for that project, that when the new roads are being built, it's bringing in people that would then cause deforestation due to the increase of accessibility.
Okay, cool. That makes a lot more sense. Thank you. Mark Sorrell just comments and says, thanks and interesting talk. And there's another question that asks, so how would you think your model would improve in a Bayesian framework?
Yeah, well, I'm not like philosophical supposition that says you have to do Bayesian or you do frequencies, that kind of thing. But for this, I just use the frequencies method. I use GRMM TNB just because it converges fast. It's quick. I think using a Bayesian framework, if I use the BRMS package, it allows me to model the response, especially the second part of the hurdle model, as being t-distributed. So if you remember the second part of the model, we are modeling a log response ratio of loss divided by, so it's just log loss divided by forest minus loss. So basically, this is meant to normalize the number, and usually it does quite well. But because in a lot of this, because we're talking about deforestation, and so there's a lot of variation across the different sub-provinces. So some sub-provinces, in some years, they tend to deforest a lot, and then in other years, deforestation might be really close to zero. So what happens is that there's a lot more variability than the variability that's expected with a Gaussian distribution. So using GRM TNB, I'm modeling this as Gaussian, but actually the tails are so wide, and really what happens is that if the tails are wide, the p-values here tells us that technically the p-values here might be a lot, sorry, not p-values, but confidence intervals might be a lot wider than what is shown here.
Cool. Yeah, thanks for describing that. So that's all the questions we have. But thanks again, Xingli, for talking today and giving us all of your whole talk and your little vignette on the the climate change and fish interactions in the Appalachians. So it was fun to see both of those, and it was learned some new things. So thanks again.
Right. Yeah, thanks for inviting me. Yeah, I really enjoyed it.
No, it was great. So thanks everyone, and next week we will have Mark Sorrell that will be giving us a talk. So thanks everyone, and see you next time. Right. Bye.
Thank you so much. Bye.